Okay, looks it's already 11:01 in both Beijing time and then United States East Coast time. So I think we can start on time. Welcome everyone to everyone on Zoom and also on both Tencent meeting or also Bilibili streaming. So today is our seventh meeting for the our SIGCOMM Paper Reading Group, and I'm the host, Xiaoqiang from Xiamen University. So today, our today's meeting is a little bit special because this is the first time our group focus on a paper it's not only is not from SIGCOMM, but also it's not even officially published yet, right? It is currently a technical report on arXiv. So the reason I took the liberty to pick this paper is because, well, I was just browsing some WeChat news and I saw this interesting news about how this tiny R1 search-to-be preview model basically use only 5% of the amount the parameters compared with DeepSeek. It's compared with DeepSeek and can already achieve comparable performance. So it's a very interesting. Maybe it's not a network paper or a system paper per se, but I do believe I briefly scanned through the technical report. I think it's a very interesting paper, and it could shed light for future research in the domain of co-design of model and the system. So that's why I sent the invitation to Yuhan Wu, one of the primary authors of this paper, and also a fourth-year PhD student from Peking University. His advisor is Tong Yang. Probably many audience are familiar with Tong's work. He has published many SIGCOMM paper, Sigma paper, ICD paper, and so on. So so today we will since this paper is very fresh. It's only posted on arXiv probably 7 days ago. So we won't have a student to present it. So instead we asked Yuhan to do the presentation, and also we will have our usual discussion session after the presentation. So without further ado, so Yuhan, you have the floors. You can start.
Okay, and thank you, Professor Xiang. And I think it's a great chance. And this technical report is quite fresh, and I think and if it's published, and it will be outdated. So I think the timeliness is more important than the completeness. Okay. So and let's start. Okay. First, and I want to clarify that this project is a collaboration and between Peking University and Jian Tech, and it's not affiliated with DeepSeek, and I will not discuss any non-public DeepSeek technologies. Okay, and the Tiny R1 was trained and released within just a few weeks, making today's content very recent. And however, it's still a preview version, and it's an intermediate outcome. And our primary focus is on developing the full version. And so, and I think the most important is the timeliness over completeness. And this is not a formal academic paper. And okay, let's dive into the details of Tiny R1. And AI and machine learning have rapidly evolved, and with large language models becoming a focus in both academic and industry. And their success is largely due to scalability and the ability to process vast amounts of data, and enabling them to perform complex reasoning, coding, and scientific tasks. However, these models have come with challenges. they require extensive computational resources and are difficult to deploy on devices with limited memory. And to address this, and we propose TinyR1, and which applies branch merge distillation to reduce model size and computational cost while maintaining high performance. Okay, let's and I think we can take DeepSeek R1 as an example. And the full version contains 600 billion parameters, and it's an astonishing number. A large parameter counts enable the model to process and generate more complex, high-quality content, making it more capable of meeting our needs. However, it comes at cost. A model of this size requires huge computational resources, making it difficult for universities and research labs or small companies to deploy. And this challenge highlights the need for smaller, more efficient models, something we aim to solve with TinyR1. And so we can start from what's knowledge distillation, and it's a widely used model compression technique. It allows us to transfer the knowledge from a large and powerful teacher model to a small and more efficient student model. And the primary goal is to reduce model size while retaining high performance and making it an efficient solution to the challenges of deploying large models. This process consists of two stages. And first, acquiring knowledge from the teacher model, which has been trained on large data sets. Second, transferring this knowledge to a small model, enabling it to perform similarly while using few resources. And this method plays a crucial role in creating smaller, faster, and more deployable AI models. Next, we will explore how the branch merge distillation method builds upon this concept. And in the first phase of the distillation process, and we acquire knowledge from the teacher model, DeepSeek R1. And we begin by collecting high-quality seed data, and primarily consists of university-level problems in math and coding, programming, and science. And these problems come from open source datasets. And we send the above seed data to R1 and collect its responses, and which include chain of thoughts. And this means that instead of simply generating final answers, the teacher model breaks down multi-step reasoning problems into smaller structured steps, simulating the way human solves problems. And in the second phase, we transfer the teacher model's knowledge to the student model through fine-tune. And fine-tuning allows the student model to adapt and learn from the teacher model, enabling it to replicate reasoning strategies and problem-solving approaches while using significantly fewer resources. And this step ensures that the student model maintains high performance despite being smaller and more efficient. Next, and we will explain the fine-tuning briefly. And it's a process that adapts a pre-trained language model into a specific downstream task using a small amount of high-quality data. And the key advantage of fine-tuning is that it can enhance performance on specific tasks with a small amount of high-quality data. making fine-tuning a highly efficient technique for optimizing large language models. And for TinyR1, we use DeepSeek R1 distillation and 32 billion as the base model, and apply a full parameter fine-tuning using carefully collected open source data. The fine-tuning process helps the model develop stronger abilities in solving math, coding, and science problems. However, to further enhance model performance, we introduce a new method called branch merge distillation. And this technique allows us to improve accuracy and efficiency. And in this phase, we focus on 3 key domains: math, coding, and science. And our one challenge in training large language model is dealing with mixed data. And this refers to training data sets that combines multiple domains, forcing the model to learn everything at once without clear distinctions. The problem with mixed data is that the model struggles to identify common patterns across different domains, leading to a non-optimal generation and weaker task-specific performance. To solve this, and we introduce branch merge distillation. First, fine-tuning separately for each domain allows the model to learn domain-specific knowledge efficiently. Second, merging the model with a model merging technique ensures that the final model retains the strengths of all domains. And this method significantly improves training efficiency and performance. And here we show the sources of data we used, and all the questions come from open source data sets, and the answers are generated by DeepSeek R1, and there are no noteworthy technical details, and you can just follow this detail and train your model. In the merge phase, we use array fusion to combine models from different domains into a single unified model. And this is an algorithm designed to merge one model into another of the same structure. And to explain this process, we define 2 models. First, base model. The primary model that retains after merging is the main structure, and the second is the base model, the model that contributes parameter to the base model. And during merging, some parameters of the base models are dynamically replaced by those from base model. And through our experiments, we found that array fusion outperforms other model merging techniques, resulting in a higher scoring merge model. And this highlights the effectiveness of our approach in maintaining strong multi-domain performance. And compared to other 32 billion size model, TinyR1 surpasses existing model in math, coding, and science. And what's remarkable is that despite using only 5% of parameters of DeepSeek R1, and TinyR1 achieves comparable performance in math, demonstrating its efficiency. And recently, Qianwen from Alibaba released the QWQ model. And while our class 1 score is lower, and our internal testing show that Tiny R1's class 8 score is higher. And what does this mean? And class 8 measures how often the model gets a correct answer within 8 attempts. A high class 8 score suggests that Tiny R1 often finds the right answer, just not always on the first try. This indicates strong reinforcement learning potential. And reinforcement learning can be used to bridge the gap between pass 8 and pass 1 to further enhance model accuracy. And that means, I think, if we use reinforcement learning techniques, and the Tiny R1 can surpass Qianwen QWQ. And here we show our experiment results on different model merging strategies. And we found that directly mixing training data makes it difficult to optimize 3 domains simultaneously. And some trade-offs occur, preventing this model from achieving peak performance in math, coding, and science at the same time. However, model merging techniques provide a solution. By merging specialized models, we can retain domain-specific strengths and while achieving the best overall performance. Moreover, model merging is a promising area for academic research, and unlike training on mixed data, and merging requires much lower computational resources, making it a practical approach for universities and research labs to explore. Okay, finally, we are committed to open sourcing our code and datasets too. Additionally, our technical report already provides extensive details for those interested in our model. Look ahead, and there are several key areas for future research and improvements. First, we can use Qianwen instruct models as the backbone model. And second, you can apply our method to 14 billion size model and other model sizes to enhance scalability. Third, and you can expand high quality supervised fine-tuning data, which plays a crucial role in boosting model performance. Fourth, and you can explore more advanced, more merging algorithms, which could further refine knowledge integration. And we just use the default parameters of the Irene fusion. I think there's a huge space you can do in this area. And finally, you can leverage reinforcement learning to optimize model and decision making and improve accuracy. And we believe this direction will help push Tiny R1 to the next level. And we welcome collaboration and exploration from the research community. But I think the most challenging one is the fifth, the reinforcement learning, and it requires quite a lot computational resources, and it may be not quite suitable for a unit for lab in a university. But I think the first four directions and it are visible for the labs in the university. Okay. Okay. Let's my presentation. Thank you.
Oh, sorry, I muted myself. Sorry. So yeah, Yuhan, thanks for the presentation. I think it's quite interesting. I think there may be some echo. Oh, that's fine. Yeah. So for from the audience, I don't know if you are researcher or students. If you have any questions, you can either raise your hand or just directly speak. Or if you're a little bit shy, you can also just type it in the chat. So, but while we're waiting for other audience questions, let me open the floor with a couple of questions I have myself. So let's start. Let me start with your last future direction. You said applying reinforcement learning to further optimize the performance of the model. But you also commented that it could be very computationally expensive, so that might not be affordable direction for university, right? I think that's what you said, right?
Yeah.
So my question is, are you referring to apply reinforcement learning for your branch and merged model, or just for any other large language model in general? So is there any basically say we want to work apply reinforcement learning on tiny R1 compared with, say, we apply reinforcement learning for maybe DeepSeek R1 or DeepSeek 671B R1. So which one is harder or more expensive in your opinion?
I think it depends on the number of parameter. Yeah. If it's a 32 billion size model, and you want, I think that's almost the same cost. But the improvement, I think, personally, I think the improvement space depends on the difference between the pass 8 score here. I mentioned the pass 8 score and the pass 1 score. For the same size, Qianwen QWQ, that's a 32 billion model, and Tiny R1, the difference of their pass 8 score is different. I think from this aspect, QWQ is more harder.
I see.
Yes.
Okay, cool. So my next question would be, so you can you go back to your slides, maybe slide number 12 or number 11?
Okay.
There's one, yeah, the one you talking about how to aggregate or how to merge the model. I think there's one slide. Yeah, can you go to that slide? I don't know which one is it. Maybe slide.
Here?
Oh yeah, the merging phase. The merging phase. So you mentioned that you used yeah. So you maybe slide number 11. So because there you mentioned you are using in Tiny R1 you used arXiv fusion to merge the model. Right. Oh yeah. Sorry. Slide number 12. So, yes. So what makes you make this design decision? So for example, do you have you tried other merging methods or methods, or is it based on your experience, or you just try a bunch of different ones and Archifusion just happens to give you the best one? What's the rationale behind that?
Yeah, actually, we tried many model merge algorithm as shown in a figure 2.
Mm-hmm.
The left one is arXiv, and it gets the highest score. And the other the other methods are lower than it. But this experiment is it's not strict. It's not a strict experiment because here we only test the GPQA scores. It's about the science ability. A better way is to test both test all the 3 score, GPQA and math ability and coding ability. But at that time, the science ability is the most weak. So we try to find a algorithm that can get the highest science score. And actually, we did. And look, that's 68 score, right? And you can see this. You can see this table. No, wait.
Right.
You can see this table.
Yes.
It's 68. Right. It's much higher than our release, the preview version, and 68 is very close to the full R1. The full R1 gets 71 score, right?
I see.
So actually, our preview version is just intermediate outcome, and we have better model, but and we release an intermediate model. Yeah.
Right. I see. So a follow-up question on that matter is in this the branch and the merge design. So yeah, because I don't work on machine learning or large language model. I'm mostly still focused on networking. So I'm a little bit old school. So but I'm trying to understand what's the motivation for you guys to use like the branch and merge. I think intuitively it really makes sense, right? So you fine tune the model with in different tracks, essentially different tracks, right? Coding, math, and science. So basically, you branch, and then after you fine tune them, and then you try to essentially try to merge them. So basically, making one model to possess the capability on the for solving for tasks of different tracks, right? So is this you guys invention, or it has been explored in the machine learning community before?
First, this algorithm is not invented by us, and it's just an open source tool, and this is it's not even it's not even a paper. It's just an open source repo, code repo. And our okay, maybe I can start from the traditional method, and a common method is in the fine tune is to use data mixture and different groups and different groups focus on different domains and maybe and they different groups find find good data and which is reflected from the domain specific model. Okay, a different group of people, and we'll try to find good data and train a high score domain specific model, maybe math model, coding model, science model, and a common way is that after they find the good data, they will mix this data and fine tune again from scratch and to train a good final model, a good mixed model, and it's time consuming, and we notice that there are some algorithms can merge models, but actually I think model merging it is not a it is not widely acknowledged in the industry, and most company use I think most company use a data mixture, and but we find that model merging has a very good performance and it's fast because you can see you just need 4 GPU hours to merge the model, while data mixture need to train all the data again together. And I don't think that and I don't think data mixture is an efficient way. I think model merging is better.
But as you just said, the industry didn't use model merging a lot, so there must be a reason for that, right? Is it because we can clearly observe that the model merging consumes much less hours than data mixture, but what's the downside of model merging, I guess? So what, for example, what's the what's the key reason why industry haven't thought about using model merging until you guys just did it? I guess there must be some reasoning behind that, right? So do you happen to know, or maybe it's also a mystery to you guys too?
And I think maybe I can answer from 2 aspects. First, in the industry, and for a good final model, you need to solve the problems in many domains, not just 3. Okay. And here we just focus on 3 domains and 3 benchmarks.
Right.
In the industry, they focus on 10 or 20 benchmarks. But the model merging method can only merge 2 models. Okay. If you train 10 domain specific model, I think maybe it will be a problem about how how you merge this model, at which sequence. Now we can try. Now here we try. We first merge math and coding model in the first step, and then we merge it with science model. And we can merge math and science model in the first step, and in the second step we merge it with coding model. But if but what will happen if we merge 10 models? And I don't know. Okay. I think that's the first reason.
Right.
And the second is that I think there is no such a big gap between model merging and data mixture. And model merging will take more time for model developers to do experiments. And I think those big companies, they don't care so much about GPU hours, and they care about their developers' time. Okay, so and so I think most big companies use data mixture, but I think in the university and model merging is worth trying, because it needs much less GPU hours, and I think the students have more time to do these experiments.
Right. So yeah. So I guess I think I totally buy the first reason. So essentially, your first reason is like merging models that may require, well, basically, I suggested by this figure, the order of merging could make a difference.
Yeah.
So there may be certain like so-called the optimal order of model merging, right?
Yeah.
So and it because still we are in the exploration phase, so we do not know, or at least so far there is no like universal principles or rules about like what in what order we can we more in what orders model merging works the best. I guess still like still an open problem, I guess, right? That's your first reason, right? And but the second reason I don't quite maybe I don't fully understand yet. Is because you said well the tech giant companies like Microsoft, OpenAI, and so on, right? They don't care about the GPU hours, but still, right? So it's like at least suggested by this figure, like 740 hours versus 4. Still, that's a very giant gap, right? That's a very giant reduction of GPU hours. So yeah, or maybe as you suggested, so maybe data mixture is more about like engineering, maybe a little bit more engineering efforts, or that's my guess, right? So, but really to make sure model merging can fully bring out the can fully function well, still requires a lot of thinking and research, and so maybe people haven't really thought through that yet. Is that right?
And I think those companies like OpenAI, they care about GPU hours, but they care about those the big parts. the big part is pre-training and or reinforcement learning, and
Right.
not this part. And the 700 GPU hours they can use 100 GPU to run at the same time, or even more. They have thousands of GPUs, so so they don't care about the GPU hours in this part.
I see. Okay, yeah, that's I think that's a very interesting question. So, yeah, I think there's a question actually from one of my students. So still, because in our group paper reading group meetings, we always ask a similar question, like, what's your aha moment about when you were designing Tiny R1? Like, hey, maybe you sit there, discuss it with your group mates for like with your team for maybe half a day or a couple of days, and then eventually, hey, you figure it out, right? So, or maybe you are doing a little bit more try and error, and eventually find, hey, this one intuitively makes sense and performs well, and then maybe this is the right way to go for the first step. So what's it like? What's like a behind the scenes story we're working on this?
Okay. The most interesting time is that we find that after merge the three model, our math score rise from 73 to 78, and that's out of our expectation. We used to expect that if it's larger than 70, we will be happy. But it reaches 78, and that really makes us astonishing. Yeah, and about the aha moment, often now often refers to the pattern change in the reinforcement learning process, and our model is based on Distill R1, and so it has it already has the ability to generate COT and think a long time. So okay, so let's do different concept.
I see. So in your experiment, like, you have three domains of data, right? Math, coding, and
Yeah.
science, right? Three domains of data, three domains of models. So which domains data has the greatest impact on it? It's the same. It's the follow-up question from the question about aha moment. And also, I need to clarify that the question is not from my student. It's actually from a user called Zhu He. I don't know if that's the real name or just a screen name. It's because maybe she's on she or he is on the Tencent meeting room, so she's not with us on Zoom at the moment. Yeah. So, which domain's data has the greatest impact on the final performance of your merged models?
I think it's hard to compare, because we find that if we train math data, and the coding score and the science score will also raise. And that's the same for coding data and science data. So it's hard to tell that which domain is the most important. Yeah.
So, but for example, let's consider. I actually following up that. I'm wondering, say we only have like a two models, right? The method coding, for example. So you do this branch, you do this branching, right? So you have two branches, one math branch and one coding branch. So after you do the branching, if I test the coding branch, the fine-tuned model of the coding branch on coding tasks, and I got a certain performance scores, and then I merge these two models, and I test the performance of the merged model also on coding tasks. Which one is it? Always the case that the merging model has a better performance, or it's not always that case?
It's not always. It depends. It's not always, and it's hard to explain in which in which case which one will be better. I think that's an open question.
I see. So I guess that's probably also related to the quality of data, right? So, and in the extreme case, say I have a fake, I have a poison model, right? So this poison model gives you all the wrong data or all the incorrect fact, all the incorrect history, and then it basically will poison the merged model, right? I guess. Okay.
Yeah.
Cool. Yeah. So we are entering our final few minutes of our meeting, but I think I know you have I think we met at SIGCOMM or another conference, right? So that's why I have your WeChat. Right? So so I know your work. You work with your group mate Kai Cheng, right? I know I work with I know Kai Cheng pretty well. So I know you guys have been working on streaming algorithms like Sketch and so on, right? And you also have you publish paper at the SIGCOMM and also ICDE and so on and KDD. So but now so SIGCOMM typically the SIGCOMM paper you and Kaicheng had essentially talks. I think still talking about sketch algorithm, right? So maybe some and it involves deploying sketching algorithm on programmable hardwares, right? So now that you're working on large language model designs, and so in your opinion, as a researcher who has stepped in both system and hardware-based implemented system, and also learning algorithm and model design, so do you see any, in your opinion, do you see any opportunities to use programmable hardwares, maybe P4 or maybe FPGA or like SmartNIC or DPU to help accelerate the whole the whole branch and merging process, basically to accelerate your system? Do you see any research opportunities there, or maybe it's just quite straightforward? It really doesn't. It really is just a very straightforward, or it's even or in your opinion, it's going to be very hard. So, what's your take on that? It's okay. You can be wrong. Don't worry. You just speak whatever you think. Yeah.
Okay. Maybe not strongly related to programmable switches and FPGA. From the system, I think from the system level now, and the LLM industry need a good reinforcement learning architecture. Then maybe that's true. Let's build on PyTorch like Megatron in training, like VLM in inference, and now we need a good reinforcement learning architecture. And I think the system about reinforcement learning architecture will be a trend in the following maybe in 1 or 2 years because it's really important.
I see. I see.
But how can we use programmable switches in a system? I have no idea yet. I think maybe it's not about programmable. Maybe it's not about switch. But I think there may be some opportunity for computation offloading and something like that in the data center. I think.
I see. Okay, yeah. I mean, you don't have to have the answer to all the questions, right? I mean, we're just brainstorming about maybe it could shed light for some of the for some of the audience for their future research, right? So no pressure here. Yeah, that's cool. That's cool. Yeah, I think our audience is a little bit quiet today, but still, I think from all the discussion here and all the presentation here, I think I think at least I mean I enjoyed the presentation and learned a lot about this one, but maybe one of the reasons is because I'm not an expert on large language model, so I'm learning a lot about this. Yeah, that's really cool. Could you maybe go to your final slide about the future research, future directions?
Okay. Oh, okay. These directions are just about 20 hours. I think in future reinforcement learning will be a trend.
I see. So one I think just a clarification question. What does SFT mean? You mean expand high quality SFT dataset? What does it mean?
Supervised fine tune. Just
Oh,
fine tune.
I see. So basically, along this direction, you're talking about like how we construct data sets with high quality, right? Because we have so much data, right? How to think, basically, what could be the quote unquote like high quality data or the most useful data, right? And how to so that we can use a smaller data set, but still can achieve the same effect of fine tune with using a larger data set, right? That's what you suggest, right?
Yeah.
Okay.
I have
a
question. I have a
go
question
ahead,
for
please.
Yuhan. How are you, Yuhan? So the question I have: Do you did you talk to people, the DeepSeek people in China? Do you work with them?
Yes. Now I work for DeepSeek.
Do you do you work for DeepSeek?
Yes.
Okay. I thought you are a PhD student.
I'm a research intern in DeepSeek.
Oh, excellent. So My question to you, which is a very simple one, how come DeepSeek manage to develop this great model with only $6 million?
Okay. Uh,
We are surprised here in the States about how did you do it.
oh, oh, okay. First, let's not about the tiny R1 model. Okay, the tiny R1 model is not trained by DeepSeek. Okay, and
Yes, I know.
DeepSeek,
I know.
yeah. Okay, then Deeps. I think the six the low cost is just training the model, and but it didn't include some other experiments. Okay. The company will use many GPU hours to, I think, maybe search parameters and validate whether the data is good. So the cost behind is much higher, and all these details, I think, um, maybe you can refer to the technical report from DeepSeek. It just report that the one model is of low cost, but there are very less high cost behind.
So what you are saying is that behind the scene, there are all sort of experimentations
Mhm.
that costs us more money than what is used to develop the model, right? There is R&D, R and research and development cost for the research and experimentation that is not included in the cost of developing the model, correct?
Yeah. Yes, and that's from my personal perspective, and I cannot tell you I cannot represent the DeepSeek company.
Okay.
Mm.
Can we get your slides, the slides about Tiny R1?
Of
Can we
course,
get the slides?
yeah, and we will read. I think we can release the slides later. Yeah.
Okay.
Yeah.
Can you
So
put
Yuhan, Yuhan, how about you send me a copy of your slides? And because all our meeting minutes and the summary will be posted on everything in SIGCOMM, our website, our Discord site. So
Okay.
everyone can just access it. Would that work for you, Hashem?
Yes, but where is the website? What is the website for this?
Uh,
Can you put it in the chat?
you mean for Tiny R1 website?
No, no. You said
Uh-huh.
you have a website for this SIGCOMM paper readings.
Yes, we have a website called everythinginsitcom.group.
Yeah,
I just type it in the chat. You just
got it.
go to that website. Yeah,
Got
and
it.
there's a
Got it.
category called SIGCOMM paper reading. So give
Thank
it
you.
a couple of days. We will post related materials on that.
Thank you very much. Thank you.
Absolutely. Mhm.
This is great. Yes. Everything SIGCOMM. Good, good, good.
Thank
Yeah.
you.
All right. So because now I think we are already hitting our 1 hour mark. So as usual, I think we will just end on time. But before that, let's thank Yuhan again for the wonderful presentation. I know Yuhan has been working really hard to finish a technical report and also prepare the slides. And he told me he's been working long hours for quite a few days. So thank you again for taking the time to talking to us. We really enjoy your talk. Yes, very interesting. And have a so. Yuhan, please have some rest, and I hope to see you soon in Beijing. Okay.
Thank you.
All right. Okay. So and for everyone, so this we will adjourn our meeting here, but we will have our next meeting in 2 weeks, and we will post the advertisement later. Thank you. Thanks everyone. Thanks Yuhan. Bye.